Hello everyone, good evening. Welcome to the session 12. Of ray optics. So today, right, we'll be able to probably wind up the refraction part, and then we'll be left with so we are currently discussing the refraction through lens, right? So this lens part we'll be able to complete today, and then we'll have to go to the optical instruments. Okay. So we were discussing about the image formation due to the lens, and we have seen the lens equation and magnification formula. We have also seen how do we calculate the transverse magnification or the longitudinal magnification and axial magnification. So what do you mean by that transverse magnification? If you have a lens like this, the magnification that will happen in terms of the height of the object, that is what we call as the transverse magnification or linear magnification. If you look at the magnification that is happening, if you keep an object on the axis, right, then for that we will talk about what? The axial magnification. So we have seen how do we find both these type of magnification in case of a lens. Continuing to that, right, in case of mirrors, we have talked about how the velocity of the object and velocity of the image will be related. If you have a mirror, if we are moving the object, right, correspondingly the image position also will change. So we can relate the velocity of the object to the velocity of the image. We have already seen that in the case of the mirror. Now what we'll do is we'll try to look at the relation between the velocity of the object and velocity of the image in case of the lens. So look at it here. We have to take a lens, right? That is why I am taking the lens to be biconvex lens, but it can be any lens. Okay, so we have a lens. We are talking about the image velocity relation to the object velocity. Here we are talking about the velocity which is measured along the axis. Okay, so think about it. If you mark the position of the object, how do you mark the position of the object? By the object distance. Generally our objects will be on the left side. The corresponding image may be on the right side or it may be on the left side. Okay, that depends upon the nature of the lens, position, etc. So let us not get into that. The position of the image, right, is represented by what? The image distance. That will be generally indicated with the symbol V, correct? We have a relation between them. What is the relation? The lens equation. What is the lens equation? 1 by V minus 1 by U is equal to 1 by F. This is the lens equation, right? Now what we will do is we will take a derivative of this equation with respect to time. Both sides we will just take a derivative. So what do we have? Derivative of V minus derivative of, not V, 1 by V, minus derivative of 1 by U is equal to what? Derivative of 1 by F. What is derivative of 1 by F? It's a constant, right? Focal length is constant. That will be 0. What is derivative of 1 by V? Minus 1 by V square into dV by dt. What is derivative of 1 by U? Minus 1 by U square into du by dt. So minus minus will become plus. We will take the negative. First term is negative, right? Second term is overall positive. We will take the first term to the right side. So what do we have? Left side will be left with 1 by U square into du by dt is equal to what? 1 by V square into dV by dt. See, what is du by dt means? The rate at which the position of the object is changing. What is this? We can call it as what? Object velocity, which is along the axis, because the rate at which the position is changing, right? That is what is the object velocity which is along the axis. Similarly, what about this one? The rate at which the position of the image is changing with respect to time. What is this? This is the velocity of the image. Both are the velocities which are along the axis. Now look at this. What do we have? 1 by u square into velocity of the object is equal to 1 by v square into velocity of the image. We are looking for the velocity of the image, right? This v square will come to the denominator. Sorry, numerator it will come to. So what do you have? V square by u square into velocity of the object is equal to the velocity of the image. So what is the formula for the velocity of the image? Vi is equal to what? V square by u square into velocity of the object. But remember, in case of lens, right, what is the magnification factor formula? M is equal to what? V by u, right? Means what is V square by u square means M square. Same formula we can write it like this also. Velocity of the image is equal to what? M square into velocity of the object. We have to keep one thing in mind. This relation is for which component of the velocity? It is for the component of the velocities along the principal axis. Okay, next we will see how we will relate the components of the velocities which are perpendicular to the principal axis. So first we are seeing what? The relation in terms of the velocities which are along the axis. What is the relation here? Velocity of the image, right, will be equal to what? V square by u square. We can also express it as what? M square. Okay, into velocity of the object. So here you can make one conclusion. When you look at this relation, right, what is the relation after all? Velocity of the image is equal to what? M square into velocity of the object. Straight away, what is the conclusion we can make? The directions of the velocities, right, both will be in the same direction, because velocity of the image is equal to M square. M square will be positive, right? M square into velocity of the object, which means what? Both the component of the image velocity along the axis and component of the object velocity along the axis, both will be in the same direction. Okay, so look at it. What do we have? The axial velocities of the image and object along the principal axis, right? What is the relation? Velocity of the image is equal to M square into velocity of the object. And what is the conclusion we can see from here? The image velocity and object velocity both will be in the same direction. Okay, now we are done with the first part, that is relating the velocities along the principal axis. Now let us go to the relation in terms of the velocities perpendicular to the axis. So again, I'll take a lens. It can be any lens. Now if, say for example, we look at the object position along a direction perpendicular to the principal axis. So we'll mark this as a point A. Now let us mark this point on the principal axis as B. If the object is moving, right, either it may be moving away from the principal axis or towards the principal axis, this movement will affect in what we can see as the height of the object, because if it is A is moving away means height of the object will be increasing. A is coming towards the axis means height of the object will be decreasing. But the movement, right, the movement perpendicular to the principal axis, right, how we can be quantified. How we can quantify? With rate of change of HO. Same way, we may have the corresponding image formed somewhere. It may be inverted, it may be erect. Okay, we are not discussing about the nature. The movement of the image perpendicular to the principal axis, right, can be quantified by what? Height of the image. But we already have a relation between them, right? What is the relation? Magnification factor is equal to what? Height of the image by height of the object. Means magnification factor into height of the object is equal to height of the image. Now take a derivative. Magnification factor into height of the object is equal to what? Derivative of height of the image. Here we are only looking at the change in terms of the height of the object and height of the image. So this is the u value, right? And this is the v value. We are not talking in terms of change in the v and u. So thereby m will be constant, right? Means m will come out. M into derivative of height of the object is equal to what? Derivative of the height of the image. So look at this. What is the derivative of height of the object? The rate at which the object is moving perpendicular to the principal axis. This is what? This is our velocity of the object, right? And what is the derivative of height of the image? Means the rate at which the image is moving perpendicular to the principal axis. This is what? Velocity of the image. But these velocities are what? The velocity components which are perpendicular to the principal axis. So what is the relation here? Velocity of the image. We're talking about the perpendicular components. Okay. Velocity of the image is equal to what? M times velocity of the object. Okay. So this is the perpendicular. Already we have seen the parallel. Parallel, what is the relation we have? Velocity of the image is equal to what? M square into velocity of the object. This is parallel or along the axis. Correct? That is the relation in terms of the velocity components. Here, the perpendicular components of velocity is, right? What is the relation? Velocity of the image is equal to what? What is it? It will be m times velocity of the object. Now here, we cannot say that both will be in the same direction. Why? Because it depends upon the value of m, isn't it? Here we cannot say that no, velocity of the image and velocity of the object both will be in the same direction. Why we cannot say? Because it depends on what is the value of the m. Okay. So look at this. Perpendicular to the principal axis, right? What is the relation? Velocity of the image will be equal to what? M times the velocity of the object. So these two formulae we have to keep in mind. The perpendicular components relation, and this is what? The parallel components relation. Parallel means along the principal axis. Okay. So this is about the relation in terms of the velocity of the image and velocity of the object. Already we have seen the same concept in the case of the mirrors. Now we are seeing it in the case of the lens. If you look at some of the past year papers, right, especially the JEE, you would see some questions on the relation between the velocities. We'll take a sample question and then we'll go to the next segment. Focal length of the convex lens is 20 centimeters. Means what? Convex lens, they say, means we will take focal length to be what? Positive, right? Find the image position and image velocity. Look at the object. Object is having a velocity of how much? 5 millimeter per second, making an angle of 37. So if this is v, I mean, it's not v, it's velocity. Okay. Because v already we use for the image distance, right? So let us not confuse. Then the velocity of the object, right? We can take the components. What will be the components? 5 into cos 37. That will be the component along the axis. What about the component perpendicular to the axis? 5 into sin 37. By the way, I think in one of the previous other problems also we have seen the value of cos 37, right? Just like our normal angles, this is also one of the very frequently used angle. What is cos 37? It will be 4 by 5, and sin 37 will be 3 by 5. What is cos 37? 4 by 5. Sin 37 will be 3 by 5. So remember we discussed about it, the triangle formed. So if you have a triangle formed with the 3 and 4 as the two sides, and hypotenuse will be 5. Okay. So here if you mark the angle opposite to the side 3, theta. So we'll have sin theta is equal to 3 by 5 and cos theta is equal to 4 by 5. What is this theta here? This is what is our 37 degrees. What is the theta? That is the 37 degrees. Okay. Now let us come to this question. So here we have the focal length. Okay. So f is equal to what? F is equal to plus 20 centimeters. And where is the object? Object always we are keeping on the left side of the lens, right? Means u will be equal to what? Minus 30 we have to take. From here we have to get the first image position, right? So we have to use the length equation. What is the length equation? 1 by v minus 1 by u is equal to 1 by f. So which means what? 1 by v is equal to 1 by f plus 1 by u. So 1 by v is equal to 1 by f means what? 20. 1 by u means what? U here will be minus 30. So if we take an LCM means it will be what? 60. 3 minus 2. So what we'll have? 1 by v is equal to 1 by 60 means v is equal to what? Plus 60. Means where is the image formed? Image is formed on the right side. Image is formed on this side. Okay. Now what about the magnification factor? This is the lens, right? What is the magnification factor? V by u, which is 60 by u is what? Minus 30. Which means magnification factor is what? Minus 2. What is the magnification factor? Magnification factor is coming as what? Minus 2. Okay, so we are done with the first part of the question. What is the first part of the question? They are asking us to find what is the image position, right? That we are done. We are able to get what is the image position. And we have also got what is the magnification factor. Why? Because we have seen the formula, right? The velocity relation formula. In that we are getting the magnification factor, correct? So that is the reason why we are also calculating the magnification factor. Okay. Now what we'll do is we will look at the formulae. Already we have them, right? Along the principal axis, what is the relation in terms of the velocity components? Velocity of the image is equal to what? M square into velocity of the object. M square means minus 2 square. Velocity of the object, what is it? 5 cos 37. Cos 37 means what? 4 by 5. So this is what? Minus 2 square means anyway it will be 4. 4 4s are 16. You know what will be the unit? Millimeter per second. Why? Because the object velocity is in terms of millimeter per second. What about the perpendicular component relation? Velocity of the image is equal to m into velocity of the object. So which means m is minus 2, velocity of the object perpendicular. Okay, what is perpendicular? It will be 5 into 3 by 5 sin 37. That will be what? Minus 6 millimeter per second. Now understand what is the significance of this minus 6. Object component of velocity perpendicular to the principal axis, we are taking it up. Means image will be down. That is what is significance of the minus. Okay. Now total velocity means what? It will be root of the component along the principal axis square. Because both are perpendicular, right? So you have velocity, we have two perpendicular components. What is the total velocity means? Root of, like the way we use x component square plus y component square, right? Whole root will come. So what is this? Root 16 square means what? It is 256 plus minus 6 square means 36. That is what? Root 292. Unit will be in terms of millimeter per second. Unit will be what? It will be millimeter per second. Okay, so is it clear, guys? What is the answers for this one? The position of the image is what? V will be plus 60 centimeter. And what about the velocity of the image? Total velocity. They are asking velocity means we have to give the total velocity, right? So we have to separately calculate what is the component of the velocity along the principal axis, and we have to calculate what is the component of the velocity perpendicular principal axis. Once we get both these components, right, then total velocity will be what? Root of, like the way we do x component square plus y component square. That way we will be able to get what is the total velocity of the object. Okay, so this is how we have to approach these questions. on the velocity relation. Okay, so you might want to club both of them, the velocity relation in case of the spherical mirrors and the velocity relation in terms of the lenses, and look at them. So whenever you're solving problems, right, try to look at, because you will have only one small difference in terms of the sign. Okay, but otherwise things will remain the same. So you might just try to club them together and then look at the equations. Okay, next is when you are having combination of lenses, right, what will be the overall outcome? Like you have a lens, you keep one more lens, you keep one more lens. This is typically that people try to do for some specific applications. Instead of having just one lens, you will try to have a combination. Like if you go to any optometrician, right, what they will do, like when they are trying to check your eyesight, like nowadays you are having these I think these digital machines that can actually check what is your curvature of the eye, and they will be able to derive what is the required lens power. But if you go to like a regular shop where you don't have all this setup, right, what they do is they will put some holding kind of a spectacle where they can keep on adding the lenses. Like they'll put one lens, maybe -2 power. If you say that you are not able to see the things properly, means they'll put one more small lens, add -0.5. if you say still not clear, means they'll put one more. Like that they will keep making combinations till you say that you are able to see the things clearly. Then that whatever the corresponding power, right, they will add up all these powers, they will add up all the powers, and that will be your overall power requirement of the corrective lens, like your eye defect, myopia, or hypermetropia, whatever it is, right. The power of the corrective lens will be decided based on that. So from that very practical observation, right, what is it that we will see when you have a combination of lenses which are put together, right, then the overall power of the combination is given by the simple addition of the powers of the lenses. Means if you have two lenses like the one here, we have lens 1, lens 2, the nature of the lenses does not matter. Total power will be equal to what? It will be P1 plus P2 and so on. If you have 3 lenses, means total power will be what? P1 plus P2 plus P3. 4 lenses means we'll add P4. F. We can also say F equivalent. What is the relation? 1 by F equivalent will be 1 by F1 plus 1 by F2 plus 1 by F3 and so on. If you look at the power, what is the power reciprocal of the focal length, right? Means P total is equal to what? P1 plus P2 and so on. That is how the formula comes. Okay, when you have combination of lenses, the image of the first lens will be the object for the second, and so on. So when you add up all the lens equations, right, we will get 1 by V. V is the final image distance minus 1 by U. This is the original object distance. That will be equal to, right hand side we'll have 1 by F1 plus 1 by F2, whatever the number of lenses we are having, all of them will be added like that. So this term is what we are calling as the 1 by F equivalent. So the effect of all the lenses combination, right, if you want to replace this with a single lens, how much focal length the lens should have? This F equivalent value. And the corresponding power is given by what? The power of that equivalent lens will be what? P1 plus P2 plus P3 and so on. So this is in terms of how do we find out what is the effective focal length and the power of combination of lenses. Here we are assuming that the lenses are together and the lenses are what? Thin lenses. Because all this while, when we are making the discussion about the lenses, the thin lens assumption is something that we are carrying. Now what will be the magnification? If the lens 1 is creating a magnification, what is it? Height of the image divided by height of the object. If the lens 2 is creating a magnification, its image height will be H2. What about the object height for the lens 2? For the lens 2, what is the object? The image of the first lens, right? Which means what? We are taking as H1. Like you can see what you have, H2 by HO. So when you have a combination of lenses, right, the overall magnification will be the height of the final image by height of the original object. That will be equal to what? Simply multiplication of all the magnification factors, m1 into m2 into m3, like that. If you multiply, means we will get what is the overall magnification factor. What is overall magnification factor? Means height of the final image that is formed, divided by height of the original object. Okay, so this is how we will see the effect of combination of lenses. Here we are keeping the lenses in contact without a gap, and of course our assumption, what is our assumption? Thin lens assumption is taken here. Okay, so this is how we will deal with the combination of lenses which are kept in contact. But not every time we may have the lenses in contact. Sometimes we may even keep the lenses at some distance. We'll see when we go to the optical instruments, right? We'll see that no, we'll use combination of lenses but which are kept on some distance. In that case, right, we are not going through the derivation. We'll just take the result, the effective focal length of this combination. So here the lenses, right, they are separated by a distance d. So what is the effective focal length given by 1 by this capital F represents the effective focal length. 1 by capital F is equal to what? 1 by f1 plus 1 by f2. See, this is what we had before when we are keeping the two lenses together. Now what is the thing that we are having? Minus d by f1 f2. So look at this now. If I say that we are keeping them together, means the d will simply become 0. Then we'll get back the same original formula. If we make the d 0, means we'll get back the same original formula, right? If we are having some distance, means what is it? The effective focal length is given by 1 by f is equal to what? 1 by f1 plus 1 by f2 minus d by f1 f2. Okay. Generally, we will not require these kind of formulae for many number of lenses. Like say you may ask, sir, what if we have one more lens with a gap d1 or something like that? Then it is better that we go with the general approach. What is general approach? We will first take the image formed by the first lens. Take that image as the object for the second. Then take that image formed by the second as the object for the third. We do the lens equation consecutively. Then we will be able to find out what is the overall position of the image and things like that. But if you just have two, right, which is normally the kind of problem that we might see. If you have two lenses which are having a separation, because this combination is there for us in the optical instruments, then what is the effective focal length value? 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2. Correspondingly, what will be the power relation? 1 by f means what? The power of the combination is equal to what? P1 plus P2 minus d into P1 P2. What is the relation in terms of power? P is equal to what? Previously what we had? P is equal to P1 plus P2, right, when we are keeping them together in contact. But here we have some distance between them. What is the power? P1 plus P2 minus d into P1 P2. Okay, so this is about finding of the effective focal length and the power of combination in case of the lenses which are either taken together. The previous one, that's the general formula. We can have any number. Power of the combination is equal to what? P1 plus P2 plus P3 and so on when we keep them together. But here this formula is only when we are having two lenses. Okay, in this, if you are thinking, you know, what if they give three lenses with gaps in between them, then what is the procedure? We better go by the usual approach. What is the usual approach? First lens will form the image. Take the image as the object for the second lens, because the rays passing from the first lens will go to the second lens. The rays coming out of the second lens will go to the third lens. Means the image of the second lens will be acting as the object for the third lens, like that. So we will take that general approach and try to find what is the final image location, etc. Okay, we'll see one question on this. Look at this one. A convex lens, power 2 diopter. Remember, convex lens focal length will be what? Positive. So power also will be positive. And a concave lens focal length 40. Means our sign convention, right? Focal length of the concave, what we have to take it as minus 40 centimeter or minus 0.4 meters. Then the corresponding, so P1 is given here, right? P1 is what? 2 diopter. P2 will be what? 1 by F2, right? What is it? 1 by minus 0.4. How much it is? Multiply numerator and denominator by 10. Minus 10 by 4 diopter. What is minus 10 by 4 means? Minus 2.5 diopter. Okay. So these two are kept in contact. Find the power of the combination. What is the straight formula, right? Check it up, guys. What is the power of the combination? P1 plus P2, because they are kept in contact, which means P1 is what? 2 diopter. P2 is what? Minus 2.5 diopter. What is totally? Minus 0.5 diopter. Means the combination, right? We are taking one convex lens and one concave lens. The combination net effect is what? How is the combination of these lenses acting? Look at this. When you see the power negative, what is the conclusion we can make? The combination of these lenses is a net acting as a concave lens, isn't it? Because the power of the combination is negative, means this is a net acting as a concave lens. Okay. They're also asking what is the equivalent focal length. So 1 by F equivalent is power of the combination, right? That is minus 0.5 diopter. Means from here what will be F equivalent? Take a reciprocal, right? 1 by minus 0.5. This is what? If you multiply numerator and denominator by 2, minus 2 by 0.5 into 2. What is 0.52 means 1. So minus 2. What is 1 by diopter means? Diopter is what? Meter inverse, right? So 1 by diopter means it will go to the numerator as what? Meter. So what is the equivalent focal length? So we get the power as what? Minus 0.5 diopter. And what is the equivalent focal length? Minus 2 meter. Just reciprocal, right? Whatever is the power we get, combination of the lenses power, 1 by power will give us what? The equivalent focal length. So here, whenever we are having the focal length of some of the lenses given in centimeter, right? We have to be careful there. Why? Because power, the unit that we are using is diopter, which is a meter inverse. So we should, like in this case, what we did, the focal length of the concave lens is given as a minus, 40 centimeter, but our convention is minus, right? We should change the focal length into meters. Then only the power will be coming us in diopter. Okay. So check it up, guys. Whether you're able to get these two values. So power of the combination should be what? Minus 0.5 diopter. And the effective focal length should be equal to what? Minus 2 meter. Let us see who can solve this question. I'll just read the question and wait for some time. I'll wait for you guys to solve. Okay. A convex lens is in contact with a concave lens. Similar story. We have a convex lens which is in contact with the concave lens. The magnitude of ratio of their focal length is what? 2 by 3. The magnitude of ratio of their focal length is what? 2 by 3. Why are they saying magnitude? Because convex lens focal length will be positive, concave lens focal length will be negative, correct? So this is what the convex to concave, that ratio magnitude is what? 2:3. So observe this carefully, what I am saying. I'll say the convex lens focal length is equal to 2x. Concave lens focal length is equal to minus 3x. Can I say that? Where x is a variable. Because they are telling me the magnitudes of the focal length, right? They are in which ratio? 2:3. One convex is 2 parts, concave is 3 parts, right? So what I am saying is I am introducing a variable. Convex lens, let us say the focal length is 2x. Concave lens will be what? because it will be negative, right? That's why we have to put minus 3x. Okay, the equivalent focal length of the combination is 30 centimeters. Equivalent focal length of the combination is what? 30 centimeters. Their individual focal lengths are, means we have to find what is this focal length. So let us call them as f1. Convex lens focal length, we are calling it as f1, 2x. Concave f2, it is what? Minus 3x. We have to tell these values. Okay, what is the information we have? Equivalent focal length. What is it? 1 by f equivalent is equal to what? 1 by f1 plus 1 by f2. This is the relation, right? When we make a combination of lenses. So what is this? 1 by 2x plus 1 by minus 3x. That is what? 1 by 2x. Denominator is 6x. 3 minus 2. That is 1 by 6x. So 1 by 30 is equal to 1 by 6x. 6 ones are, 6 5s are. Cross multiply. X is coming as 5. We cross multiply. What is the value of x coming as? 5. Means the convex lens should have a focal length of 2x, right? Which means what? 2 into 5 is plus 10 centimeters. What about the concave lens story? Concave lens is minus 3x, right? Which means what? Minus 3 into 5, that should be minus 15 centimeters. Now we have to check the options. Check it up, guys. Which of them is the correct answer? We should have one focal length as plus 10. Here the signs are also important. Convex lens focal length should be what? Plus 10. Concave lens focal length should be what? Minus 15. So look at this, which is matching. Option A. One should be having minus 15. Other should be having what? Plus 10. I'll just wait for some time so that you guys can confirm the answer. Good, Shyam. Okay, so others also you have to give the responses, because these are not very tough questions. Okay, so this is the idea of making the combination of lenses. Okay, next we might even cut the lens. Like, this is a concept that we have seen quite often. So whenever we talk about a spring in mechanics, right, we'll talk about cutting the spring. Okay, in heat and thermodynamics, you'll talk about cutting the slab, the conducting slab, we'll talk about cutting it. In capacitors, electrostatics, we'll talk about cutting the capacitor into parts by introducing some dielectric medium. In resistances, we'll talk about cutting the resistance. Same will be the case of the inductors also. So this cutting the object and trying to see what is the effect of it. So if you are trying to cut a lens, let us say we are taking a lens of focal length f and corresponding power p. We can cut the lens in two ways. One is the lens which is cut by the, you see here, the lens is cut by the principal axis. So this is what you cut the lens by the principal axis. Principal axis cuts the lens into two parts. Other way of cutting it is like this. Okay, so we'll generally call it as, you know, the axis of symmetry for the lens. Okay, transverse axis of symmetry, like that we'll use, because already we have the principal axis, right? The transverse, the axis perpendicular to it, and symmetry, that line is called as what? Transverse axis of symmetry. So if we cut it along this transverse axis of symmetry, what happens? Okay, so we are cutting it into what? Two parts. And here you can clearly see what are we forming. We are forming two plano-convex lenses. If you cut a biconvex beam into two parts, means we'll get what? two plano convex lenses. Both are identical, right? Both are identical. Now think about it. The focal length of each of them is f dash. Think about the focal length of each of them is what? F dash. We make a combination of them. We are getting what? The original length. Means 1 by f. The focal length of original length, that is like the equivalent focal length, is equal to what? 1 by f dash plus 1 by f dash. That is what? 2 by f dash. Cross multiply. F dash is equal to what? 2f. So the focal length of each of these plano convex, right, will be what? 2f. If f is the original focal length of our biconvex, these plano convex, they will have how much focal length? They will have 2f. If they have focal length 2f, means if the original lens power is p, now p dash is what? 1 by 2f, right? P is 1 by f, p dash is 1 by 2f, means p dash is equal to what? P by 2. The corresponding power will be what? Half the power. That is when, if you add both these powers, right, p by 2 plus p by 2 means we will get p. So if you cut the lens with this transverse symmetrical line, then you know the biconvex simply becomes what? 2 plano convex. Then you know the focal lengths of each of the part will be 2 times f. The powers will be what? Half. Okay, so this is about cutting the lens with this transverse axis. The other way of cutting it is what? Cutting the lens by using the principal axis. If you cut it right, you will get 2 symmetrical parts, identical. Both the parts we get will be identical. Here you know each of these parts will have the same curvature. It is not a plano convex lens. Each of them, they have the same curvature. Means if parallel rays are coming here, right, those rays will be bent and pointed to the same focal point. No difference will be there. Okay. But the thing is, if you look at it right, if the upper part is bending the rays one way, the lower part will bend the rays exactly opposite manner. The upper part will bend the rays in one way, means the lower part will bend the rays in exactly opposite manner. That is the difference between the upper part and lower part. But they would be focusing the light rays to the same point. They would be focusing the light rays to the same point, which means if you take each of these parts separate, right, each of them will be having the same focal length. Because if you pass a parallel beam of rays, means the rays will be pointed to the same point only as before. But what will be the difference? Here, if you have the full lens, right, you would be having more number of light rays getting pointed to this focus. But if it only take a part of it, what is going to happen? The image, right, the image formed will be dull because it is formed by lesser number of light rays. That is the reason if you take a lens, if you take a normal lens, they might even give some theoretical questions. They will say this much amount of lens is covered with a black surface. Means what is happening? The light rays will not be able to enter. We have covered this maybe with an opaque substance. Then light rays will still go through that whatever the remaining portion and then they will get focused. So the difference will be the image formed in this case will be what? It will be a dull image. That is what is going to happen. The image formed will be what? Dull image. So each of these parts that you are getting right, they will have same focal length. Same focal length means power also will be same. Okay. So this is the difference between cutting the lens by using this transverse axis of symmetry and cutting the lens by using the principal axis. Okay. Now once you cut the lens, we can make a combination by using these parts. We are getting the parts right. Look at it. So we cut it. We cut it means what we said, we will get 2 plano convex. We can arrange them like this, or we can even arrange them like this. Whatever way we arrange, right? Because remember, what is the power formula? 1 by f1 plus 1 by f2. Whatever way we arrange, it will be what? P is equal to P1 plus P2. which means P by 2 plus P by 2, it will be P. Here also, whatever way you arrange, right, you will get what? The power will be equal to what? P dash of the combination will be again coming as P. Means focal length, effective focal length will be equal to what? Whatever is the focal length of the original. So power of the combination will be same as the power of the original lens. And focal length of that combination, effective focal length also will be what? Same as the focal length of the original lens. So we keep it like this. That is our original arrangement, right? Once you cut it, you can still see them like they are together. They have cut, but they are still together. Or you can change the orientation like this and arrange them. In whatever we arrange, right, the total effect is going to be still the same. Okay, so the power of the combination will be same. If the power of the original lens is P, the power of the combination will be P only. Effective focal length will be equal to what? The focal length of the original lens. But when we look at the parts that we are getting by cutting it with the principal axis, right, you will get two parts. If you arrange the two parts like this, you see what is going to happen. If you arrange the two parts, right, what did we say? This is having a focal length f, this is also having focal length f. What is the effective focal length? 1 by capital F is equal to 1 by f plus 1 by f. This is what? 2 by f, means capital F value will be f by 2. The effective focal length will be what? It will be f by 2. Okay. Now power will be what? If the original power is P, means here what will be the power? P dash. P dash will be equal to what? 2 times P. The focal length is becoming half, means power will be what? Doubled. Now the interesting thing is, look at this kind of combination. What is this? One part we keep it as it is, other part is inverted. One part we are keeping it as it is, other part is inverted. Remember what we said? If one part we send parallel beam of rays, if one part is trying to bend them in one way, we are keeping the other part. I'm trying to keep them separately so that we can see what is actually happening. How this will do? If you normally pass a beam of parallel rays, means it will try to bend exactly in the opposite manner, right? Means now it will bend in the opposite manner. As a result, what is going to happen? You know, the final ray will be just coming as it is, parallel to the principal axis. If one is bending in one way, other part will bend exactly in the opposite. So if the light rays are bent like this, right, they'll be bent exactly in the opposite manner, so that the final emergent ray will be parallel to the original incident ray. Which means if you are passing parallel beam of rays, they are not going to be converging to a point. They will come out parallel. Means where they are supposed to meet, they are supposed to meet at infinity, right? So we will take the focal length as what? Infinity. This combination will give a focal length as what? Infinity. Focal length infinity means power will be what? 0, right? So if you make a combination like this, one as it is and one we keep it inverted, then what is going to happen? That combination, if one of them is trying to bend the parallel rays in one way, other will bend the opposite, exactly opposite manner. Both are identical, so whatever the deviation created in one way will be compensated. As a result of it, parallel rays will again emerge as parallel. So which means we will have to take the focal length as what? Infinity. Focal length infinity means power will be what? 0. Okay. So this is what is the difference we have in terms of the combination of the parts that we created. Okay. So the part that we have created by cutting it with the transverse axis, those parts in whatever way we arrange, we are going to have the final combination giving us the same focal length and same power as the original lens. But these two parts, right, when we keep them together in same manner, the focal length is becoming f by 2, power becomes double. If we keep them inverted, then focal length will be what? Infinity. Okay, so these are some of the cases that we need to discuss with regard to the combination of these parts made from the lenses. Now the other area is silvering of the lens surface. Like we can take any lens, so here what is it? This is a, what is it? It's a plano convex lens. For this we have coated the which part we have coated with silver? The convex part. Okay, now we can also take the same plano convex, this is also plano convex, and coat it on the planar side. We coat it on the planar side, or we can have a biconvex and coat. Generally, I mean, the way we arrange the lens is we will keep our coating on the right side. Okay, so what would happen when we silver or paint a surface of the lens? What is going to happen? Look at this. If the light rays are coming, they will get refracted at the surface 1. Here they will undergo reflection. Okay, so first refraction, second surface reflection, then they will again undergo refraction. So what is happening here? You have refraction at the first boundary plus reflection at the second boundary, again refraction at the first. So this is the general thing that we see for any lens, whether it is a plano convex or a biconvex. Any lens you take, you are silvering or you are painting one surface, means the lens now which is painted on one surface is going to act as a mirror. The lens is going to act as a mirror. Okay, now the thing is, how do we find out the image formation because of this particular lens? We are not talking about the lens now, we are talking about the lens which is already covered. One surface of the lens is covered by a silver or some paint. For this, what we have to do is, let us just say we will take the case of a lens. We have a lens here. Here what is the lens we are taking? A biconvex lens. Okay, this is the surface 1, this is surface 2. Usually the surface 2 will be the silvered or the painted surface. We are taking the object. Light rays from the object will come. As I said, they will get refracted at the surface 1, then reflection at the surface 2, then again refraction at the surface 1. That will give the final image formation. That will be giving us the final image formation. So we have to take, understand carefully, we have to take the image from refraction at surface 1. Then we have to take the image due to reflection at surface 2. Then we have to take the image due to refraction at surface 1. 3 steps. Image formed by the refraction at surface 1 will act as the object for the reflection happening at the surface 2. Image formed by the reflection at the surface 2 will act as the object for the refraction at the surface 1. 3 steps. Here we are not going to do the derivation, but if you add all these 3 equations, here refraction at a spherical boundary, reflection means what? Mirror equation. Again refraction at a spherical boundary. If you add them, then we will get this overall equation. This is the overall equation. The overall equation is for the focal length, the effective focal length of the combination. What is the effective focal length of the combination? 1 by f is equal to what? 2 times mu2 by mu1 divided by r2. So here r2 means what? The radius of curvature at the surface 2. Mu2 is what? Lens material. Mu1 is what? Because we are not going to the right side, we are only going to be on the left side and inside the material. Mu1 is what? The refractive index of the outside, which is like typically air. 2 times mu2 by mu1 divided by R2. This is the formula that we can remember. Minus 2 times of mu2 by mu1 minus 1 divided by R1. R1 is what? The radius of curvature at the surface 1. Here, like we always do, R1, R2 values, we have to substitute them by following the sign convention. What is sign convention? Anything we measure to the right is what? Positive. Anything we measure to the left is negative. So if the mu1 is equal to 1, when mu1 will be 1, if you have air outside, right, what will be the formula? 1 by f is equal to what? 2 times mu2 by R2 minus 2 times mu2 minus 1 by R1. This is the formula. If you consider the outside medium is what? Air. So mu1 will be equal to 1. But if you have some other medium, means this is the general formula we have to remember. Okay. And you may ask what we are going to do with this focal length. You want to find the image formation by this lens which is silvered. We already said this lens is now going to act as a mirror, because light rays will never go right side. Light rays will come to the left side only, right? So to understand the image formation, we have to use the mirror equation. Here we will not use the lens equation, we have to use the mirror equation. Means what? 1 by V plus 1 by U is equal to this equation we have to use, because this combination is now going to act as a mirror. The silvered lens is now going to act as a mirror, so we have to use the mirror equation. And what is this 1 by F? This is the 1 by F. Now you may have doubt, so whether this relation is only for this biconvex lens which is silvered, or it can be used for a concave lens which is silvered, or it can be used for a plano concave, or it can be used for any lens which is silvered. Like you have taken, for example, already we discussed about this plano convex, right? Plano convex, we can either silver it on the convex side. This is what? Silvered on the convex side. This is silvered on the plane side. Now when you want to use the same equation can be used everywhere. What you will have to do, look at this. If you want to use the equation here, then this is R1, right? This is R2, correct? So R1 for a planar surface, what is the radius of curvature? If you want to think about a sphere which will have this planar surface, what will be the radius? Infinity. Planar surface means R will be what? Infinity. And R2, because look at this, the second surface, right? Where is its center going to be? On the left side. Center will be on the left side. So R2 will be what? Minus R. Okay, so we have to take them along with the sign. That's it. We'll have to put R1 is equal to infinity and R2 is equal to minus R. We'll get the focal length. Once we get the focal length, means use the mirror equation. Here we have to keep in mind, we have to use the mirror equation, because the light rays will come back to the left side only, right? So this is going to now act as a mirror. Now look at this one. Here R1, the center of curvature will be on the right side. So R1 will be what? Plus. What about the R2? R2 is now planar surface. R2 will be infinity. So whatever the lens they will give, right, it need not be a biconvex lens. It can be any lens. You will just have to use this equation by taking the corresponding R1 and R2. R2 will be always our silvered surface. We have to take the R1, R2 values along with the sign convention. That is one. Second thing is, we have to make a note of the actual positioning. Like when they say that plano convex is silvered on the convex side, means R2 will be our convex part, R1 will be the plane part. So we have to keep a view on the actual arrangement. Okay, so that is how we will use the equation. So this is the equation. So this equation we can use it in any lens and we will be able to find out the focal length. And one more very important thing is, you get the focal length, you should not think that okay, you will now again go and use the lens equation, because this silvered lenses will be acting as a mirror, so we have to use the mirror equation. Okay, now look at one question so that we will be able to understand. Find the focal length of the system. So this is what, this is a plano convexa, but what is the surface that is silvered? It is the plane. Now as I said, we'll have to remember this formula. What is the formula? 1 by f is equal to what? 2 into mu 2 by mu 1. Here outside is air, right? So what is the formula? It will be mu 1 is 1, mu 2 is what? 1.5. Okay, and look at this. What is our this is surface 1, surface 2. What is R1 means? The center will be on the right side, so R1 will be equal to what? Plus 40. R1 value will be equal to plus 40. What about the R2? Second surface is plane, right? Means R2 will be infinity. R2 will be what? Infinity. Okay, so we'll just have to substitute. So what is it? So 2 into mu 2 by mu 1, 1.5 by 1 means 1.5. 2 into 1.5 divided by R2 is what? Infinity, which is entirely anything by infinity is what? 0, minus mu 2 by mu 1 means 1.5. 2 into 1.5 minus 1 divided by R1. What is R1? Plus 40. So what you have here? This is minus 2 into 0.5 divided by 40. Minus 1 by 40. This is 1 by f. 1 by f is minus 1 by 40 means f is equal to what? Minus 40. So this silvered lens is now going to act as a mirror of how much focal length? Minus 40. Means this will tell us what is the nature of this mirror. Focal length negative means what? It is going to be acting as a the overall behavior will be what? It will be like a concave mirror, because focal length is coming negative, right? Means what? The overall behavior is going to be like a concave mirror. So this is the equation that we need to keep in mind. What is it? The 1 by f is equal to what? 2 times mu 2 by mu 1 divided by R2 minus 2 times mu 2 by mu 1 minus 1 divided by R1. In this, from case to case, what will change? The curvature values will change. So depending upon the lens given to us, right, the curvature R1 value, R2 values will change. Only thing we have to keep in mind is R1, R2 values we have to substitute along with the sign convention. That's it. So then we will be able to get the focal length. Once we get the focal length means we have to keep in mind that this focal length is going to be now used just like the equation of the mirror, because the overall behavior of this lens is now going to be like a mirror. Okay, so this is about the idea of silvering of a lens. We'll continue in the next class. In the next class, right, we have one small part which is left about the lenses, that is the aberrations. Like when the image formation is happening, right, sometimes we may not have a clear image being formed, and there will be some reasons for that. Okay, so we'll see, that's mostly theoretical aspect. We'll see that, and then we will get into the optical instruments. Okay, we'll see in the next session.